I have on hand to read. So what we'll do is go to the whiteboard first and foremost and totally, if it'll come up. Okay, whiteboard's here, but while we're waiting, let me move my taskbars out of the way. This is smack in the way here down here. Y'all are a little in the way. Jesus, scoot over to the right just a tad. There, I've got you. Alright, and the taskbar up here is also in the way, so let me move it out of the way as much as possible, and then move my whiteboard, which y'all probably just see a white screen and you think, what's he moving? I have a limited whiteboard, so I give as much white space as possible. Okay. Hopefully, James will be coming in, so if you sense or hear or find out from him that he can't get in, let me know. I'll see if I can do anything to remedy that. All right, we are in Chapter 1, Systems of Linear Equations, in Section 1.2, Gaussian Elimination and Gauss-Jordan Elimination, and we're on page 19, getting ready to start Example 7. Now, example 7 is also located at larsonlinearalgebra.com. You go there for an interactive version of this type of an example. And I believe I pointed this out to y'all before. I try to do it every class. But this new 8th edition, excuse me, I've got hiccups now, of elementary linear algebra by Ron Larson has both larsonlinearalgebra.com, absolutely free website. You don't need a code, you don't need a class key, you don't need anything. Just go to it. And there you see, like these examples here, interactive examples, and you'll see some other things there too. Homework exercises, the odd number of those are found at calcchat.com. And I'll usually say that when I'm assigning the homework problems. Odd number homework problems at CalcChat. So if you weren't aware of that, there they are. Now, here's example 7. Let me get my Wacom and my pen, and let's write it down. Again, lots of writing with linear algebra, repeating things over and over again. Here is your system of equations. X minus 2y plus 3z is equal to 9. The pen does strange things. Okay. Negative x plus 3y is equal to negative 4. 2x minus 5y plus 5z is equal to 17. Now, if this looks sort of familiar, we've seen this before. Okay. Now, where do we go from here? All it says, well, what it says is use Gauss-Jordan elimination to solve this system. Now, I think we've solved it before using Gaussian elimination. I think we solved it before just by using row operations or equation operations on just the equations before we even did matrices. But now we're doing Gauss-Jordan, so that means get it into a matrix. Can any of you tell me what that matrix will be? Okay, it's the coefficient matrix 1, minus 2, 3, augmented with the solution matrix or vector 9. Minus 1, 3, 0, always put a 0 in if there's a blank, -4. And 2, -5, +5, 17. Now, I hope I copied everything right. If I didn't, please catch me and tell me. I don't want to get miles through into the problem and find out I missed a sign somewhere. So keep up with me. Now, Gauss-Jordan elimination starts out just like Gauss elimination. What we want in the upper left corner is a 1. And guess what, folks? We got it. It's there already. Already one step into the process. Okay? Now we're going to call that a leading 1. Okay? Now, what we want next is zeros below that leading 1. Okay? Just like Gaussian elimination. The first one's real easy. We're just going to add row 1 to row 2, and that will give you the new row 2. Okay? So we're using that top row with the leading 1 in it. Leave that alone. Write it down. 1, -2, 3, 9. Okay? Add the 2 rows together to get the new row 2. That gives you a 0. That gives you a 1. How nice. This gives you a 3. And this gives you a 5. I'm pretty happy there. Okay. Now, what we want is a 0 down here as well. Using that leading 1, that's what we usually do, is use the leading 1 to do it. So let's take that, multiply it by -2, so when you add to that, it becomes a 0. Oh, here comes James. So I'll admit him to the class. I'll mark him on the roll. And by the way, folks, last night I stayed up late getting everybody in the roll book. So you're now in my roll book. There you are, right there. Little bitty class. Okay? 3 students. 100% attendance, way to go. Now this morning, my first class was well attended, but that's a class of almost 30. I think we're down to 28 students now. So I don't know, we had more than 20. So it was a decent number there. In my second class, I've had 18 students who have been coming. All 18 of those were there today. There are 2 students still listed in the class who early in the term did something in Blackboard, so they got noted that they had submitted the syllabus agreement, okay? Syllabus acknowledgement page. I never saw it. They just did something, so it showed up in Blackboard. So I could not count them absent that first week. I had to make them present. They've never shown up since, ever. So now I can easily imagine they'll say we never attended the class, and they haven't. They're being absolutely true. They did do one thing on Blackboard, and therefore they got counted present. I don't like this system, but it's what we're doing now. So folks, well, y'all are probably all getting ready to graduate, so you won't have to worry with this anymore. But if you know of students coming up behind you, or friends or relatives, neighbors, sisters, brothers, whatever, please, if they're not going to attend the class, if they are going to attend, they have to do something that first week, or else they get removed. But if they're not going to stay with the class, don't do something that first week, so you can get removed and you won't get charged anything. It's a mess the way we do it, and it's just, there's got to be a better way. I don't know what that way is, but guess what? This is the last term I have to worry with it, so sorry about that. All right, so what we're going to do to get this one to become a 0, James, we're in Chapter 1, Systems of Linear Equations, Section 1.2, Gaussian Elimination and Gauss-Jordan Elimination. We just are starting in Gauss-Jordan Elimination on page 19, Example 7. That's where we are now. We wrote down the system of equations, we wrote down the augmented matrix, and now we're reducing that augmented matrix. We got a 1 here that was already given to us. We got the 0 there. We just did that with adding row 1 to row 2. Down here we're going to multiply row 1 by -2, add it to row 3. That will make a 0 down here. That's what we want. So it's -2. This drives me nuts. -2 row 1 plus row 3. Okay. So -2 times 1 is -2 plus 2 is 0, exactly like we wanted. -2 times -2 is +4, -5 is -1. -2 times 3 is -6, plus 5 is also a -1. This should be looking familiar. And -2 times 9 is -18, plus 17 is also -1. All right, let's do a little review here. We wanted a 1 there, we got it. We wanted zeros here, we've got it. Next, go to the second row. The first non-zero entry we want to be a 1. We've got it. Now with Gauss-Jordan elimination, with Gaussian elimination, we go right here and try to get this to be a 0. That'd be easy to do. But with Gauss-Jordan elimination, we want zeros above and below the leading 1. This one didn't have anything above it, so we only wanted zeros below it. So here, let's first do 2 times the row 2, add it to row 1, and that will make a 0 here. It won't change this because we've got that 0 there. So like I said, twice row 2 plus row 1 becomes the new row 1. All right, so here's what happens there. This time, since we're using row 2 with our leading 1, we'll write it down. 0, 1, 3, and 5. We're changing row 1, so let's do the change. 2 times 0 is 0, plus 1 is 1. See, we didn't lose a thing there. But 2 times 1 is 2, minus 2, that gave us our 0 there. Good, that's what we wanted. 2 times 3 is 6, plus 3 is 9. Ooh, that's getting big. And 2 times 5 is 10, plus 9 is 19. Boy, that's getting out of hand, isn't it? All right, move on. We got our 0 above it. We want a 0 below it. How do we get this to be a 0? Use that leading 1. Add row 2 to row 3. So that's it. Just row 2 plus row 3 is the new row 3. So add them together. 0 plus 0 is 0. 1 plus -1 is 0. 3 minus 1 is 2. And 5 minus 1 is 4. Good deal. Now, we're at the point right now with Gaussian elimination, we're almost through. Not quite now. Let's review what we've got and what we want. We wanted a 1 here. Got it. Zeros below it. Got it. We wanted the first non-zero entry in row 2 to be a 1. We got it. Zeros above and below it. We got it. Next, go to row 3. We want the first non-zero entry to be a 1, not a 2. So what we're going to do is row 3 divided by, quit that. Go back. Okay. Divided by 2. And that will get it for us. Now I want to, and if it's okay with you, I'm going to do it right here. Divide this by 2, divide that by 2. Okay, so this stays a 0, that stays a 0. This becomes a 1, and this becomes a 2. Now I know that's ugly, but can you forgive me for being lazy? Probably not, but I'm going to do it anyway. I need to find my eraser. Where is it? There it is. Okay. All right. So I'm going to erase this and that and write in 1 and 2. So I didn't have to write all those numbers again just to do that. All right, Gauss elimination, we'd be through. We'd say z is equal to 2, then do back substitution and figure out what y is and what x is. Gauss-Jordan elimination, we want to get these to change to zeros. So how do we get this 9 to become a 0? Minus 9 times row 3 plus row 1. So that's going to be the next step. Minus 9 times row 3 plus row 1. Okay? So let's see what it gives us. Okay, since we're using row 3, we're going to write it down. 0, 0, 1, 2. And by the way, that tells us right there z is equal to 2, just like it did in Gaussian elimination. We've got one of our 3 answers. Let's go about the others. So, minus 9 times 0 is still 0, plus 1 is 1. Didn't change that. We didn't ever want that to change. Minus 9 times 0 is 0, plus 0 is 0. Good, we didn't want that to change. Minus 9 times 1 is minus 9 plus 9 is 0. That's exactly what we wanted there. And minus 9 times 2 is minus 18 plus 19 is a 1. Guess what? X equal 1. Okay? But let's not stop there. We got a 0 here, right here. We need a 0 there. Okay? So in this case, we'll do row 3 using that leading 1. Negative 3 times row 3 plus row 2. Get out of there. Goodness gracious, this is driving me nuts. Okay. Minus 3. Yuck. I don't know what's wrong with this thing. Minus 3 row 3. There, it did it again. Row 3. It did it yet again. Why is it doing that? I don't know. Row 3 plus row 2. All right, finally. So minus 3 times 0 is 0, plus 0 is 0. Good, we didn't want that to change. Minus 3 times 0 is 0, plus 1 is 1. Good, we didn't want that to change. But minus 3 times 1 is minus 3, plus 3 is 0. That's exactly what we wanted there. But minus 3 times 2 is negative 6, plus 5 is minus 1. So what's our answer? Write it down. X equal 1. X equal 1. I can't get this to go away. This is enough to drive you nuts. X equal 1, Y's equal minus 1, and Z is equal to 2. Okay, let's see if that works. I think we've checked this before. 1 minus 2 times minus 1 is plus 2. 1 plus 2 is 3. Plus 6 is 9. That works. Minus 1 plus 3 times minus 1 is minus 3. Minus 1 minus 3 is minus 4. That works. 2 times 1 is 2. Plus 5 is 7. No. Yeah. And plus 10 is 17. Yes, that works. There's our solution. All right. So let's look and take a big picture here. Gaussian elimination basically will give you that last, whatever that last leading one that you have here, it gives you an idea of what its answer is. Then you take that, back substitute, and as you go you find out what the next leading one will be, what the next leading one will be, always back substituting to see what you got. Gauss-Jordan elimination just takes a couple of more steps in your row reduction to do what we call reduced row echelon form. And what that gives you is ones, or at least leading ones down here. Every leading one has zeros above and below, so you can just read off the value. This one's equal to that, x equal that, y is equal to that, z is equal to that. No back substitution involved at all, which is sort of nice. Couple more steps here to do, miss several more steps here. Which is easier? Which is faster? They're about equivalent, but this gives us 1, -1, 2, exactly like they got. Now, they bring up a point here, which is a very good point, kind of a sad point, but a good point. What if your first system of equations looked like that? Okay? Now, what's the first thing I notice there? There's no coefficient of 1 for any of my x's. Okay? Which means from the very beginning, you're going to have to divide one of those equations by its leading coefficient to get a 1. In the first one, you get a 1, 5 halves, 7. The second one, we get a 3, 2/3, 1, 3. And the third one, we get a 1, -4/3, 0, 6. Well, frankly, I just as soon have one of the latter two rather than the first one. The first one had 2 fractions in it, the other two had 1 each. So you have to just weigh your options, okay? What do you want to do? How many fractions you want to worry with? Because when you're doing row reduction with fractions, that gets a little nastier. Still legal, you got to do it, but it takes a bit more effort. So you just have to notice you're going to wind up with fractions sometimes, and sometimes they can get kind of messy. The next discovery at the top of the page actually has one of those that doesn't have any leading ones, but there's something else sort of special about it. Let's do that discovery. Okay, this is on page 20. It says, without performing any row operations, explain why the system of linear equations below is consistent. Okay, here's the system. 2x sub 1 plus 3x sub 2 plus 5x sub 3 is equal to 0. Next one, minus 5x sub 1 plus 6x sub 2 minus 17x sub 3 is equal to 0. The third equation, 7x sub 1 minus 4x sub 2 plus 3x sub 3 is equal to 0. Now, how can you, just by looking at that system, I don't know what the dinging was there, just by looking at that, tell me that system is consistent? What do we mean by consistent? It has at least one solution. So can you tell by just looking at that system of equations that it has at least one solution? Anybody? James, your light's on. I don't know if that meant you meant to answer or not. Anybody? Okay, here's the giveaway. Notice what all your constants are at the end. If I can get my pen, they're all zeros. So guess what? If x1 is 0, x2 is 0, and x3 is 0, guess what? No matter what those coefficients are, when you multiply them by 0 and add it to something multiplied by 0, add it to something multiplied by 0, you're going to get a 0. Same thing here, here, and here, 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 and here. They're all going to be 0. So guess what? 0, 0, 0, that's called the trivial solution, is a solution for all three of those linear equations. So it has at least one solution, the trivial solution. That makes it consistent. All right. Now, here is discovery number 2. I'll try to write this. I guess I'll write it down here. You know what I'll do? Because this is exactly the same set of equations. So we've already answered that question. So what I'm going to do now is, I wish I could just bundle them up and do them, but I can't, so I'll do them this way. Everything else looks the same, except we're adding 2x of 4 here, and that's still equal to 0. Here we're subtracting 3x of 4. That's still going to be 0. And here we're adding 13. I don't know. Does anyone know what that dinging is about? And that's equal to 0. Now, this system has more variables than equation. The question is, why does it have an infinite number of solutions? Now, maybe you didn't know it did, but it does. Well, we know it has one solution still. 0, 0, 0, 0, 4 of them this time. That will make every one of those equations equal to 0. But if you were going to do a Gaussian or Gauss-Jordan elimination, which I hope we're not, okay, we'd wind up with a 1 here, zeros below it, may wind up with a 1 here, and zeros above and below it there. We may wind up with a 1 here with zeros above it, but then we'd have arbitrary numbers here. We couldn't do anything else with them. So guess what? This has, we know one solution, okay, and you could have some parametric form here that gives you an infinite number of solutions, because you don't have enough equations to come up with a unique solution. Anytime you have more equations than unknowns, if it has a solution, now if it doesn't have a solution, hang it up, it's not going to have a solution. But if it has a solution, it will have an infinite number. And this one does. Now, that's just taking it at my word, but that's indeed what's happening. Now, let's do example 8. I think I'll erase what's on the screen now. Is that okay? That was just a discovery thing. We'll get to that much later in the course. We'll use that thing we just talked about. Here's example 8. 2x of 1 plus 4x of 2 minus 2x of 3 is equal to 0. 3x of 1 plus 5x of 2, they say is equal to 1. All right. Now, this differs from the discovery. If this had been a 0 here rather than 1, yuck, I didn't mean to do that. Okay. If this had been a 0 rather than a 1, you'd know it'd have at least one solution, and because it has 3 unknowns, only 2 equations, it would have an infinite number of solutions. However, that's not necessarily true for this being a 1. So we're going to have to proceed. Now, I really hate it when they give you problems like this, because there was absolutely no reason in the world to write the problem like that. If you knew that 2x of 1 plus 4x of 2 minus 2x of 3 is equal to 0, you also know divide everything by 2. That would have been my first step, but I say, why not do it here? Divide it here. 1, 2, minus 1. Why not do it there? So that's going to be, I'm going to do it in that first row, because you can do that. Divide everything by 2, and that gives you your leading 1, so there's an advantage there too. And that gives you a 1, 2, minus 1, 0. Okay? Second equation, 3, 5, 0, 1. All right. To do Gaussian or Gaussian elimination, excuse me. I just about lost my voice there. Squeak, squeak. I'm hoping a little carbonation will break it up. Don't know if it will, but it tasted good. Okay. So let's see what we got. Either Gauss-Jordan or Gaussian elimination, we got to get this 3. We got a leading 1 now that we divided by 2. Okay. And that came out with no fractions too, which was very nice. To get this to become a 0, we need to multiply the top one by -3 plus this one. So -3, row 1, plus row 2 is now the new row 2. Okay? So we're using that leading 1 in row 1, so we leave that row alone. 1, 2, minus 1, 0. Now I skipped that step just because I have a very limited room to write, and it's also hard to write on this screen, this little pad. Okay, over here, -3 times the top plus the second. That would be -3 times 1 is -3 plus 3 is 0, of course. -3 times 2 is -6 plus 5 is -1. And we get -3 times -1 is +3 plus 0 is 3. And we get -3 times 0 plus 1 is 1. Okay. Now, we got a 1 here, leading 1 here, 0 below it. Got it. We want a 1 here. Well, we got a -1. We'll multiply this row by -1, or divide the row by -1. I don't care, but that makes this a plus, that a minus, and that a minus. Okay? Good. Now, leading 1, 0 below it. Leading 1, we need a 0 above it. So let's do that. Okay? We're using the second row, the one with the leading 1 in it now. 0, 1, -3, -1. Now, how are we going to get this to become a 0? -2 times the second plus the first. So, -2 times row 2 plus row 1. -2 times 0 is 0 plus 1 is 1. Good, we didn't want that to change. -2 times 1 is -2 plus 2 is 0. That's exactly what we wanted it to be. And minus 2 times minus 3 is positive 6, plus 6 is 0, and minus 2 times minus 1 is plus 2, plus 0 is 2. Have I done something wrong here?
Why is you multiply negative 3 times 0 and you got negative 1?
Yeah, I did something wrong. Okay. Let me go back and see. Did I copy my problem? Oh, I'm on the wrong page. No, I'm sorry. Here we go. 1, 0. Am I on the right problem here? Okay. That's a 1, 2, minus 1, 0, 3, 5, 0, 1. Okay. Yes, I did something wrong here. Okay. Was it here?
Yeah, in the beginning, how you
Yeah.
went
Minus,
0.
yeah. Minus 3 times 3 is minus 3 plus 3 is 0. Got it. Minus 3 times 2 is minus 6 plus 5 is minus 1. Okay, and minus 3 times a minus 1 is 3. So that gave, yeah, this is right so far. And that would be, yeah, okay. I think it was in the next step. Okay, and it's a minus 2 times row 2, add it to row 1. Minus 2 times 0 is 0 plus 1 is 1. Got it. Minus 2 times minus 3 is positive 6 plus 1. How did I get a 0 there? I mean, I don't even know.
On the first one, you know how you multiply negative 3 times 0? How did you get a 1? A negative 1?
Okay. All right, now where? Right here?
No, in the beginning.
Right here. Negative 3 times row 1, add it to row 2, right? So negative 3 times 1 is negative 3 plus 3 is 0. That gave you a 0 there. Now, remember, I did negative 3 times 2 is negative 6 plus 5 is negative 1. That was a minus 1 there.
The last one, keep going.
Okay. Minus 1, minus 3 times a minus 1 was plus 3, plus 0 was a plus 3. And this was a minus 3 times 0 is 0 plus 1. That was a plus 1. It was a minus 1 plus 3 plus 1. I wanted a plus 1 here. So I multiplied, I didn't write it down, minus row 2. I just negated row 2, made that plus, that minus, and that minus. Okay. I did it, I said it, I didn't write it down. Okay. I was just saving steps. I should have not done that. Here's where I made my mistake here. Minus 2 times 0 is 0 plus 1 is 1. That's correct. Minus 2 times 1 is minus 2 plus, get out of there. I don't know why this is changing. Minus 2 times plus 1 is minus 2 plus 2 is 0. That's correct. Here's where I don't know where this came from. Minus 2 times minus 3 is plus 6, minus 1 is plus 5. And I don't know how I wrote a 0 there. I can't write a 5 though. That is so ugly. Okay. That is a 5. Okay. And then minus 2 times minus 1 is 2 plus 0 is 2. So that's right. All right. Now, okay. Oh, okay. I'm sorry. I was thinking this was one with no solutions. I said, this got solutions. It's got plenty of them. But you see, we don't have a leading one here for x3. So this is where we have to assign a parameter. Remember, the favorite parameter of all time was t. So we're going to assign let x3 equal t. Just some parameter t. Okay? So this line right here says x sub 2 minus 3t is equal to minus 1, which when you add 3t to both sides, that tells you x2 is equal, because this adds to 0, is equal to 3t minus 1. I just don't like leading off with a minus number. This top equation says x sub 1 plus 5 x sub 3, but that's t, 5t, is equal to 2. So when we subtract 5t from both sides, what we get is, this adds to 0, we get x sub 1 is equal to 2 minus 5t. Okay, so what's our ordered triplet? It's 2 minus 5t, comma, 3t minus 1, comma, t. Pick a t, any t. T equals 0. You get 2 minus 1, 0. That works. Go back and plug it in. Pick any other t, 1. That gives you a minus 3, 2, 1. Plug it in. That works. Pick another t, minus 1. That gives you 7, minus 4, minus 1. That works. Okay? Any t. You have an infinite number of solutions. Okay? That's what was bugging me. I thought the title said no solutions, it said infinitely many solutions. So, now, a lot of times when you have more equations than you have, more unknowns than you have equations, a lot of times you will wind up with infinite number of solutions. Not always, but most of the time you will. If you have more equations than you have unknowns, either one of those equations is basically meaningless, and it'll turn out having a row of all zeros at the bottom, and you may wind up with a unique solution, or you'll wind up with no solutions, or you may wind up with an infinite number of solutions. So you could have all three cases then. But if you have more unknowns than equations, you either probably are going to wind up with no solution or an infinite number of solutions. I just don't see how you could ever come up with a unique solution then. So, just something to keep in mind. Now, I've asked this every time. I know what it was last time, but I don't know. Some of you can't look at a book right now, is that right? Yay or nay? Okay, you cannot look at a book, right? Okay, so I don't know how much of this I need to write down, but I will. We're going to run into a term here, and by the way, for you folks, I think all three of you are in differential equations too. We'll run into the same concept in differential equations. You may have already run into it in earlier courses as well, but a system of linear equations in which each of the constant terms at the end is 0. Like if this 1 here had been a 0, this would have been what we call a homogeneous system of equations. A homogeneous system of m equations in n variables always has the form of whatever your coefficients are, they're all there, okay? But everything on the right is 0, okay? All of your constant array there, your constant vector, every one of the elements is 0. Remember when we did the discovery on the previous page, on page 20? Both of those were homogeneous systems of equations. All the constants at the end, not the coefficients, the constants, were zeros. Okay? Now, a homogeneous system must have, this is in our discovery, must have at least one solution, the trivial solution. If all those constants are 0, set all the variables equal to 0 and you got a solution. Guaranteed. That's the trivial or obvious solution. Okay? Now, after that, that may be the one and only solution. It may be one of infinite number of solutions. But that one will never have no solutions. It always has at least one. So let's do example 9. So let's clear the screen here. Well, I'm on the wrong pad. Let's clear the screen. All right. Here's a system of equations. X sub 1 minus x sub 2 plus x sub 3. Okay, what's that sound? Oh, no, that's 3x sub 3 is equal to 0. Okay, 2x sub 1 plus x sub 2 plus 3x sub 3 this is really ugly writing, the pen just keeps skipping on me, is also equal to 0. That's a homogeneous system of equations. Okay, now I had a student in a class, maybe about a year ago or so, I think it was a year ago last summer. He, for some reason, did not like the term homogeneous. He wanted to call it homogeneous. In fact, I think it was a couple years ago. A student said, "Isn't that homogeneous?" Okay. I thought, well, surely it probably can be pronounced that way. So I started saying it both ways, either homogeneous or homogeneous, however you like to call it. And I had a student later in my class who pulled up her phone that has some sort of app on it that tells you how to pronounce words, spelled it in for them, and they said homogeneous. Okay, so we're back to being homogeneous. It was a couple of summers, summer before last, the student just really didn't even like the term at all. But that's beside the point. Okay, so let's set up our matrix so we can try to do things. So the augmented matrix would be 1, minus 1, 3, 0. 2, 1, 3, 0. Excuse me. Sorry. Toward the end of the week, I just felt running out of steam. I mean, it's been, every week is a long week. Of course, part of it's my fault. I'm teaching 7 classes. 3 of those classes are 4-hour classes. One of those is a mini term with a lab, so that's 4.5 hours twice a week. The 2 other calculus classes are 4-hour classes, and then my other 1, 2, 3, 4, 5 classes are 3-hour classes. But that's still, it runs me down. Okay. All right, let's start our elimination. The good news is we have a leading 1 in the upper left corner. So that tells us we can, to eliminate this and get that to become a 0, you do minus 2 times row 1 and add it to row 2. Alright, so let's do that. Yuck, get out of there, quit doing that. You probably couldn't see it, but my screen started jerking around. Okay, because the pen went in the wrong place. So, goodness, I can't talk. We're using the first row, that's the leading 1 row, so write it down. We don't ever change that while we're using it. 1 minus 1, 3, 0. Now the one we're changing is the second one. Negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times negative 1 is plus 2 plus 1 is 3. And negative 2 times 3 is minus 6 plus 3 is minus 3. And guess what? Negative 2 times 0 is 0 plus 0 is 0. That 0, those zeros will never change. No matter what elementary row operation you do, they are going to remain zeros. I don't think I need to hold the book anymore, and it's really awkward, hot, everything else. Let me get my pad alone. Alright, so what do we want to happen next? Okay. You've got a leading 1 here, 0 below it, good. You want this to be a leading 1. Hey, that's pretty easy to do. Let's divide everything here by 3. So that's going to become a 0, 1, minus 1, 0. So if it's alright, I'm going to erase the 3's over 3's and write them as 1's. 1 and minus 1. Okay, and that is a 1. Why the pen did that, I don't know. So we've got a 1 here, 0 below it. We got a 1 here, though it may not look like a 1. That is a 1. We want that to become a 0. So how do we do that? Pretty simple. Row 2 plus row 1, that will do it. So let's do that. Row 2 plus row 1, and that becomes the new row 1. So let's do that. Let's keep row 2 alone. 0, 1, minus 1, 0. Goodness gracious, I'm about to lose it. My whole head is clogging up. I don't know what's going on here. Okay, so let's do row 2 plus row 1. 0 plus 1 is 1. Good, we didn't want that to change. 1 minus 1, 0. That's exactly what we wanted to happen there. Minus 1 plus 3 would be a 2. And 0 plus 0 is still 0. That never changes. Alright, so what do we have now? X sub 2. Oh, no leading 1 for the third column. Any column without a leading 1, that becomes your parametric column, your parameter. So let's let, this is where we begin, let x sub 3, it won't always be x sub 3, but it is a lot, equal to that parameter, whatever you want to call it. They like to call it t. So then we can write this down. X sub 1 plus 2t is equal to 0. So all you have to do is subtract 2t from both sides, and that gives you x sub 1 is equal to minus 2t. Okay, down here you have x sub 2. Yuck. I'm looking in the wrong place. Goodness, you would think I just started using this. Erase the wrong part. Alright. Man, I'm so sorry. My head just feels nuts. Okay. That's x sub 2 minus t is equal to 0, which means x sub 2 is equal to t. So this is add t to both sides. I didn't do that, but hopefully you knew that's what was happening. Those add to 0. Okay, so what's our ordered triplet? Our ordered triplet is minus 2t, t, t. Okay, there it is. Pick a t, any t. Obviously, the one we knew already, 0, 0, 0, works. And it better work because it was a homogeneous set of equations. But negative 2, 1, 1 works. 2, negative 1, negative 1 works. You know, pick a t, any t, and you can come up with the ordered triplet that works. Okay? Yeah. Now, that illustrated the feature, and since some of you don't have a book, let me go on and write this one down. I think I've got time. Yeah, I do. So this time I'm going to type in some text here so you'll have it. Okay. This is theorem 1.1. Every homogeneous system of linear equations is consistent period. Moreover, if the system has fewer equations than variables, then it must have infinitely many solutions. Now, this was basically exactly what that discovery was leading us to get. Both sentences here were included in that discovery. The first of those, every homogeneous, not Jurius, I don't know what that is, homogeneous system of linear equations is consistent. You know it has at least one solution. All of them, the trivial solution, everything's equal to 0. Moreover, if the system has fewer equations than it has variables, I like to say it the other way, more variables than it has equations, then it must have an infinitely many solutions. So there is your first theorem in this section. And that finishes this section. So homework exercises here would be any of the odds 1 through 5. They're all at calcchat.com. They're all in the back of the book. The answers are. CalcChat, you'll see worked out solutions of how they got those answers. 7 or 9, both at CalcChat. 11 through 17, any of those odds, all at CalcChat. Any of the odds 19 to 23, they're all at CalcChat. Any of the odds 25 through 37, all at CalcChat. Now these next two, 39 and 41, they say you might need to use a software program or graphing utility to solve these. They are a little on the hairy side. Not totally impossible, but a bit time consuming, we'll put it that way. 43 or 45 should both be at CalcChat, and 47 should be at CalcChat. Now, excuse me, 49 should be at Calc Chat, and 51 should be at Calc Chat. Okay, let me back off from that. Yeah, 51 should be at Calc Chat. 53 should be at Calc Chat. 55 should be at Calc Chat. 57 is a writing exercise, so if you want to look at that, you can, or read what they do in Calc Chat. I assume they'll have it there. 59 is a true false, so you can look at that. There's 4 pieces to it, so there's actually 4 true falses. Okay. 61 is another writing exercise. You can either do something with that or just read what Calc Chat has. 63 should be at Calc Chat, and 65 should be at Calc Chat. And then there is 67 should be at Calc Chat, and 69 is a writing exercise. If you don't want to do it in the you can either read what they write about it at Calc Chat if they have it there, or you can work it up on your own, or you can forget about it. It's up to you. So let's move on to 1.3. Applications of systems of linear equations. Now, the first of these is called polynomial curve fitting, and it certainly is an application. It's a very tedious application though, and since we're already a bit behind on time, I'm inclined to not do this one at this time. But let me just give you a few pointers about it. If you have a curve like that one, notice it has 1, 2, 3 relative extrema. A relative minimum at the bottom, which looks like a absolute minimum. Then about in the middle of it is a relative maximum, and then a little to the right of that is a relative minimum again. Okay? Now, that indicates to me that graph should be able to be matched with 4 points. Okay? If you pick out any 4 points on that, okay, you should be able to get an exact match, because that would be represented by a 4th degree polynomial. Now they show 1, 2, 3, 2 that they don't number, and 1 that they call the nth number. You only need 4 to precisely match that. Anything less than 4 will come pretty close to matching it. Anything more than 4, you may have things that don't match at all, but you'll see. Now, example 1 is showing a quadratic, which is a 2nd degree polynomial. They give you 3 points on that, and they say find the polynomial. Okay, well, I'm sorry, I guess they're saying you need 1 more point than what you have. I was thinking exactly number, but I guess you do need n plus 1. So for a 4th degree polynomial, we'll need at least 5 points. For a 2nd degree polynomial, you'll need at least 3 points, okay, to get an exact match. Okay. The rest of their examples, they're just saying find a polynomial that fits these 1, 2, 3, 4, 5 points. You're going to have a 4th degree polynomial. Okay. Then they show how to translate. When you have very large numbers, you can do some adjusting to them. Like if you have 2011, 2012, 2013, rather than using those big numbers like that, you could say 11, 12, and 13. Those would be much smaller numbers, just understanding that you do have, at your final answer, be sure you put a the 20 in front of those. Or the way they suggest it is when you have huge numbers like that, pick either the middle number or a middle number and set that to 0, so you're subtracting 2013 from that one, so subtract 2013 here, 2013 there, 2013 there, 2013 there. You're going to wind up with a -2, -1, 0, 1, and 2. Okay? That makes your curve fitting much better. But at the end, you go back and put in the 2000 and blah. You add the 2013 back in at the end. Okay? Now, a very interesting example, application of curve fitting, is given by this one. The mean distance from the sun, the period of revolution, you get some really hairy numbers with your 4 planets there: Mercury, Venus, Earth, and Mars. Okay? You got 4 points there. You should be able to come up with a cubic polynomial that will match those. Okay? They actually say try it with a quadratic polynomial and you still get a very good match. Not exact, but very good. The one that's off a little bit seems to be Mars. Mars doesn't quite fit quite as nicely as the other 3, but it's a very, very good fit. Okay? And obviously a guy named Johannes Kepler did that kind of stuff, and when he did, he was able to determine that there was a really good relationship there. It wasn't that it fit a quadratic particularly well, it did, but he found out that the mean distance a planet is from the sun relative to its period fits in a log transformation perfectly, or very close to perfectly. Okay? And that's why I wasn't going to do too much with this. Sorry. I don't know what's happening. I'm just having trouble breathing. It shows another thing. Sometimes a transformation, this one would be a log transformation, winds up making data fit very, very nicely. Well, Johannes Kepler found out that the square of this one thing is proportional to the cube of something else. Well, that's kind of messy to try to set up something that will work. However, you do a log transformation, now you have a linear relationship there, and sure enough, these 4 planets with that log transformation, they line up perfectly, and that's from a log transformation. Now, there's also a linear algebra applied at the bottom. Researchers in Italy studying acoustic noises, and guess what? They use linear algebra. We've been to Rome a few times, and you talk about some loud traffic. It has some pretty loud traffic. Fortunately, when we've been there, we've been able to stay at places off the main thoroughfare, so we don't hear all that noise. Now, I kind of glossed over polynomial fitting. It certainly is an application of linear algebra, matrix, that kind of stuff, but it's really, really tedious. And usually you get computers to do it for you, so it just becomes very tedious doing it here by hand. However, the network analysis we are going to do, and this is on starting on page 29. And the reason we're going to do network analysis is, I think all of you probably have already finished Physics 214, or are you still in 214? Any of you? Oh, you finished it. Have all 3 of you finished it?
Yes.
Okay, well then, this is following up with that. It's reinforcing that. When you did Kirchhoff's laws, and I bet you did them, didn't you? Of circuits, that was network analysis. But in many other instances, you'll be doing network analysis. So the first few examples won't be that applicable to electrical networks, but they'll be applicable to any networks. And these are usually fairly reasonable to do. Here's a simple network, okay? And in that network, you see your input is coming in, what do they call that? 25 is coming in, okay, to your node, and going out from your node is X1 and X2. Well, guess what? You can't power up things in a node, okay? So you know that X1 and X2 are both leaving, so therefore X1 plus X2 has to equal 25. And that's what they express up above. Very simple network analysis. The next one, however, example 5, is a little more complex, and we have 1 minute to do it, don't we? We're not going to get it done in 1 minute. So that's where we'll pick up next time with network analysis, example 5. Okay? And then we'll move on and do Kirchhoff's laws, which you have had in physics. Homework exercises here in this section, there's really not many that you need to do because we really didn't do the polynomial curve fitting. You can look at some of them if you want to, especially if this is something you think you might run into in the future. I never have in that many circumstances. On my doctoral dissertation, we did do a little bit of this, but it was just sort of minimal. But you could look at any of the odds 1 through 11 if you wanted to. You could look at 15 if you wanted to. 17, 19, if you want to look at those. We'll pick up next time with 21. So you got plenty to work on in 1.2, 1.3. You don't have to do any of these. But let me say this. Should have said it yesterday in yesterday's class, because I think all 3 of you were in that. I forgot to, so I apologize for that, but I will say it now. I'll say it slightly differently than I would have yesterday. Good news, bad news situation coming up. The bad news is Monday's a holiday. So the good news is it doesn't affect us any. We'll still have class Tuesday and Thursday of next week, only miss Monday. If you were in yesterday's classes, which you were, I would have said it differently. Good news, bad news situation. The good news is that Monday's a holiday. The bad news is we'd be missing class. So for your Cal 3 and your differential equation, we will not have class on Monday. This class, though, we will have class both times next week. And so don't expect to see an invite for either of those 2 classes. They're not going to show up for Monday. However, you will get an invite sometime, maybe even today, for next Tuesday's class. Okay, just because I don't have anything else going on this weekend or Monday. So I'll send out the invites for Tuesday's class today, probably by the end of the day. It'll be late today, very late. All right, any questions? I do want to say this. I don't know if I said it yesterday. Really, please be careful, be safe this weekend. I know it's a holiday weekend. I know it's Labor Day. It's a good time to get out and visit with friends and family. But please, please be safe. Keep the mask. Keep the social distancing. I'll tell you this. I won't call any names. But I got a phone call from one of my instructors, full-time instructor. She has 5 classes this term. They're making most of the full-time instructors go to campus 2 days a week. Why? It makes no sense. But they're making them do that. They don't make me because of my health situation. But they're making them go to class 2 days a week. Yesterday, when she went to campus like she usually does on Monday, Wednesday, when she was met at the door with the guy with the officer with the thermometer, she had a temperature. She was told, turn around, go back home, go to the doctor, go get tested. The odds are, I mean, hopefully not. Maybe it was just a cold or something, but this is not a season when you expect to have a temperature. If she wound up with COVID because she was forced to go to campus every Monday and Wednesday, I'm not going to be a happy camper at all, because now she probably has a miserable 2 weeks ahead of her, and she probably won't be able to teach all her classes. All of her students will suffer. She will suffer big time, and maybe the rest of us can pick up and do some of her classes for her. I don't know. It's not going to be pretty. There was no reason she had to be on campus. Now, maybe she picked it up at a grocery store or something like that. No way of telling, but it's inexcusable that they made her go to campus, and then if she caught COVID there, inexcusable in my mind. So, folks, be safe, be careful, take it easy. Don't force situations that might get you in trouble. Okay, I'll just leave it like that. Have a good weekend. Okay. I'm going to stop sharing unless there's any last questions, parting shots. Anything? All right. Well, then I'll end the meeting. Y'all have a good, safe weekend. Okay? Take care. Bye-bye.